Okay, exercise number 6, part A. We have to find the order of this 4 cycle. Of course, we could just look at part B and say, well, it's 4, we are going to prove this, but here we want to familiarize ourselves with the powers of sigma. So sigma squared is sigma applied after itself. So we have 1, 2, 3. So we plug in the 1 from the right. 1 goes to 4, 4 goes to 2, so 1 goes to 2. Oh, this is a transposition. 3 goes to 1, 1 goes to 4, so 3 goes to 4. And let's check, 4 goes to 2, 2 goes to 3, so 4 goes to 3. All right, so the square of this here is no longer a 4 cycle, this is interesting, but a product of 2 disjoint transpositions. So let's find sigma to the 3rd power, which is sigma squared. So 1, 2, 3, 4, and then composed with sigma. So let's plug in the 1, 1 goes to 4, 4 goes to 3, 3 stays where it is. Okay, let's look at the number 3, 3 goes to 1, 1 stays where it is, and 1 goes to 2, so 3 goes to 2, 2 goes to 3, 3 goes to 4, 4 stays where it is. Oh, the 3rd power is a 4 cycle again. And number 3 and 4, the length of this cycle, have no common divisors. So, and now we would expect that sigma to the 4th power would be the identity. This is a sigma to the 3rd power composed with a sigma itself. 1 goes to 4, 4 goes to 1. So 2 goes to 3, 3 goes to 2, and the same for 3 and 4. So this is indeed the identity. So the order of sigma, either to be defined as the smallest natural number that gives me sigma to this number is the identity, which is clearly 4, or we can define it as the number of elements of the cyclic subgroup generated by sigma. So the order of this element is 4. And now, of course, we would expect that a 5 cycle has order 5 and so on. And this we are going to prove in part B. There's a hint, it's quite obvious, but the notation is a bit awkward. So without loss of generality, we assume sigma is of this form. This is a little bit cheated, but after relabeling the A1, A2 and so on, we can assume that sigma has this form. The idea of the proof stays the same. All right, now the key to the proof is this here. What does this mean? So, sigma to the kth power applied to L. L is any number between 1 or m, or if this isn't general enough for you, you could write A sub L and here A sub k plus L. Now what does this mean mod m, or as explained in the hint, the smallest remainder modulo m? This means the following. If, for example, I take k to be 1 and L to be m, what would I get? By this equation I would get 1 plus m, but 1 plus m is no longer a number in this cycle here. So I have to reduce it mod m, taking the smallest remainder, which would be 1, and this is exactly what happens because the last number gets mapped to the first number. And this is the key to the proof, to understand this. And then this here is actually obvious, because what happens if I take sigma squared by this equation here? I have to get 2 plus m mod m, meaning 2. This is exactly what happens because sigma has moved m to 1 and then 1 gets moved to 2. And this is 2 modulo m. The smallest remainder mod m is 2. So this is exactly what happens, what this m cycle does. And then of course sigma to the k of L is simply k plus L. So this clearly describes exactly what the powers of this cycle here do. And now we have to ask ourselves, when is the first time that this here gives me the identity, so the number doesn't get moved at all? Clearly, if k is less than m, something happens all the time, every number gets moved. But for the first time, in the case k equals m, what do I get? I get sigma to the m is m plus L, but remember we always have to reduce modulo m. This clearly gives me L. L is a number between 1 and m, so this is the smallest remainder, mod m. So this means for the first time sigma to the m of L gives me exactly L mod m. And this is true for every number L between 1 and m, or for every a1 up to am. This would be the more general proof. Okay, so I hope the idea became clear. I apologize for not writing it down more formally. I simply don't want to. And I hope you don't have to do this on an exercise sheet that you have to hand in, because to write that down to convey your ideas is a bit tedious, and well, I don't want to do that right now. So I hope this was clear enough. And from now on, we simply take this as a fact. A cycle of length m has exactly order m. All right. No need to be disappointed or even angry. Let's write it down neatly. So we take this cycle here, cycle of length m, and we are going to prove that the order of this cycle is m. So first of all, we show that for any number that is less than m, or less than m minus less than, oh that's difficult, or less than or equal to m minus 1, that sigma to the kth power cannot be the identity. And this is important because the order is the smallest number, besides 0, smallest natural number, that gives me sigma to the m, or to the order, is the identity. So what happens? For example, if k is 1, then I simply apply sigma to a1. By definition, this gives me a2. What is sigma squared of a1? Well, I apply sigma once, that gives me a2, and then sigma twice, that gives me a3, and so on. So this here is a sub k plus 1. And this always works without leading to the beginning of this cycle, because by assumption the maximal value for k is m minus 1, and in this case I would get here a m, the last entry. So, but those are obviously distinct. So this here is not the same as a1, and this already means that this here cannot be the identity, because the identity would leave all the elements fixed, but it doesn't leave a1 fixed. So sigma to the k is not the identity for all those numbers here. Now we have to show that sigma to the m actually is the identity. Right, for a1 this is easy, because this would give me a m plus 1, but the cycle ends here, so by definition we go back to a1. So if I apply sigma m times to a1, I end up with a1. So this means sigma to the m leaves a1 fixed. And all that is left to do is to show that this is actually true for all the other a's. All right, I think I have it. Sigma to the m leaves a1 fixed. Now for the other ai, let I be an index between 1 excluded. up to m, m included. So then, this is the important trick. This looks difficult, but really is not if you think about it. In an example, sigma to the m of ai, we have to show that this is ai again, because then sigma to the m leaves all the ai's fixed and hence is the identity. So now we decompose sigma to the m. M can be written as I minus 1 plus m minus I plus 1. If you put that all together, you simply have m. Now, why? Because if I apply this to ai, I end up with a1. And if I apply sigma I minus 1 times to a1, a1 simply gets pushed to ai. This is what I wanted to show. Okay, now breathe. Let's make an example. For example, I equals 2. So in this case, this decomposition is I minus 1 is 1, m minus I plus 1 is simply m minus 1. So now here, what happens? I apply sigma m minus 1 times to a2. If I apply it m minus 1 times to a2, let's do another example. Let's take m equals 4. So I apply sigma 3 times to a2. 1 time, 2 times, 3 times. So I simply end up with a1. And now if I apply sigma this 1 time to a1, I end up with a2. So sigma to the m of a2 is a2. Or another case would be I equals m. Let's see. In this case, this decomposition becomes sigma to the m minus 1. And here simply sigma to the first power, so sigma itself. Why? Because m minus m is 0, so here only sigma remains. But what is sigma applied to am? This is clearly a1. So here I have sigma to the m minus 1 of a1, and this again is am. Also in this example here, m equals 4, so I have to apply sigma 3 times to a1. Once, twice, 3 times, so I end up with a4. All right. So this is the complete formal proof without any cheating, without any relabeling, and without any hand waving. Now you have to judge for yourself. Was it enough to see the idea with the modulo m and to say, well, all right, that's true, or is this better for you? Of course, if you have to hand this in, this exercise, you should try to write it down as formally as possible, but I think this step here, this requires some experience. This is not so simple. Always start with an example, concrete example, and then try to formalize or to generalize to general exponent. All right. So in part C, we are supposed to find the order of this product of two disjoint cycles in S7. Now we just learned this here has order 4, this here has order 3. And we are looking for the smallest natural number such that the kth power of this here becomes the identity. Now, very important fact is, because they are disjoint, they commute. And then we have learned way back that if I'm in an abelian group or if I have two commuting elements, then the kth power of those elements is simply the kth power of the first element composed with the kth power of the second element. Very important. And only if they commute, which they do, because they are disjoint. So now we have to find the smallest number so that both sigma to the k and tau to the k are the identity. Well, this is not true, because without them being the identity, the composition still could be the identity. So we have to think about that. A little more. But now all the powers simply interchange these numbers that we have here. There can't be any new numbers. So also the powers are disjoint. This is important. And now it is impossible for disjoint permutations to combine to the identity, right? Because this here, for example, moves number 1 to something, but then here nothing can happen to the number that number 1 is moved to, because this number will not be in this cycle here, because they are disjoint. So to be the identity, actually both powers need to be the identity and don't move any of the numbers. This is important. Now, what could we try? We could take k is equal to 4. Then this would be the identity, but this here not. You can try it for yourself. This will not give you the identity. Why? Because tau to the 3rd power is the identity, so tau to the 4th power is identity times tau, which is not the identity. We could try 3 here, but sigma to the 3rd power is not the identity. So an obvious choice would be 3 times 4, because then this contains a 4, giving here the identity, and this contains a 3, making tau being the identity. So this here would be sigma to the 4th to the 3rd power, composed with tau to the 3rd. And this here is a general power law that holds in any group, abelian or non-abelian. We proved that a long time ago. So this here is the identity to the 3rd power, still remains the identity, and this here is the identity to the 4th power. Okay, but wait a minute. If we call this composition here pi, then we know that pi raised to the 12th power is the identity, but the order of this is the smallest number such that this holds. The smallest natural number, so 0 excluded. Now, the key to this exercise is really in the hint. If pi to the k is the identity, then we know that the order of pi divides k. It need not be k. K can be greater. But from this, because this, if this is the identity, then those guys already must be the identity, as explained before. But that means, again by the hint, that the order of sigma divides k and the order of tau divides k. What does that mean? Well, that means k is a common multiple of those orders. But now 12 is the least common multiple of the orders 3 and 4. Therefore, pi to the 12th power is the identity actually for the first time, so 12 is the order. And now all we have to do is to formalize this to 2 general disjoint cycles. So our claim would be that the order of a cycle is the least common multiple of the orders of the cycles. This would be the claim. Okay, let's try the general proof, and for this we first prove the hint. Now about the skulls or the difficulty of this exercise, make no mistake. If you've seen this before, if you've learned algebra before and you know these tricks, then this is not too hard to come up with by yourself. But the problem sets are intended, as well as the videos, for real beginners that have had no contact with abstract algebra before. So I think to come up with this, if you see it for the first time, or if you've never done it before, this is pretty difficult. So as always, if you could solve this on your own and haven't seen these tricks before, please comment below and I'm going to congratulate you. So we let the order of a permutation, or any group element, be S, a natural number, not a 0, because then it would be the identity. So to avoid trivial stuff, we say S is a natural number, so S is not 0. Okay, S might be 1 if sigma is the identity, but this is the trivial case. So then the following is true. If sigma to the m is the identity, then I know that S must be a divisor of m, or m is a multiple of S. So to prove this, we divide m by S with remainder. That means I can find natural numbers q and r. R might be 0, q of course not, such that m can be written as q times s plus r, and the important thing is r is less than s. Yeah, I pull out factors of s so long until the remainder is smaller than s. That's the idea. And now keep in mind s is the smallest natural number such that sigma to the s is the identity. Okay, now we take a look at sigma to the mth power. M can be written like that. And now we apply the power rules that hold in any group. First of all, this plus here becomes composition, which I write as a dot or as a circle for composition of maps. And sigma to the qs can be written as sigma to the s to the qth power. This is always true in any arbitrary group. But sigma to the s, by definition of the order, is the identity, and the identity to any power is still the identity. So I end up with sigma to the r. Now, if I assume that this here is indeed the identity, this is only possible if r is 0. Why? Because r is less than s, because s is the smallest number with this property here. So this only leaves the possibility that r is 0, but that means if r is 0, that means m is q times s, and this by definition means that s is a divisor of m, or m is a multiple of s. And this proves this hint here in both directions, because you could read this backwards here. Okay, this already I think is not too easy for a beginner to write down. And actually later when we talk in the lessons about the order, we are going to call this a proposition and prove it again, I think. Okay, with this in the back of our heads, we try to prove the following result. So we assume that a permutation is the product or composition of two disjoint cycles. I should have written that here. This is important. Disjoint cycles. This here is a k cycle. So by what we just proved before, its order is k, and this here is an L cycle, so its order is L. And of course you can generalize this easily to a product of arbitrary many cycles, but that only blows up the notation and is not really necessary. And now we claim, as in the example before, that then the order of this permutation here is the LCM, the least common multiple of k and L. As in our example before, we had 4 and 3. 4 times 3, because they are relatively prime, is the least common multiple, and this turned out to be the order. And this is a general result that we want to prove. All right, now we have to be very careful about our notation. So first of all, we let the order of this permutation here be S. So we abbreviate by S, and we call the least common multiple of the numbers k and L simply M. So what do we have to show? We have to show that S equals M. This is what we want to show. And remember, a property of the least common multiple is if k divides any number and L also divides that number, or that number is a multiple of k and the number at the same time is a multiple of L, then because M is the least common multiple, then M already divides this number. This will be important. Okay, now first of all, we raise pi to the power of m, m being the least common multiple. Then pi is sigma tau. I now stop writing the composition circle. And now very important, because they are disjoint, they commute. We thought about that before. And for commuting elements, this power law holds. This is not true in general, but if the elements commute, I can write it like that. Now, m is a multiple of k and l. So I can write this as sigma to the k times whatever x and tau to the l times y. And then by the power rule that holds generally, this is sigma to the k to the x and tau to the l to the y. But by definition, sigma to the k is the identity, tau to the l is the identity. So this here gives me the identity. So now this means pi to the mth power is the identity. So by this claim here, s, the order of pi, must be a divisor of m. In particular, s is less than or equal to m. All right, next, by definition, s is the order of pi, so pi to the s, of course, is the identity. Again, because those guys commute, pi to the s can be written as sigma to the s composed with tau to the s, and this is still the identity. And now, this means that these already have to be the identity themselves. Why? This is very important because the cycles are disjoint. In general, for every permutation, this is true. Pi to the s times pi inverse to the s is the identity, because those guys commute, they're always the identity, so I can pull the s out. So this is true, but of course pi to the s or pi inverse to the s need not be the identity themselves. But because those cycles are disjoint, all their powers are also disjoint. They have no numbers in common that they move. So if this here leaves all the numbers fixed, then this can only be the case if those powers already leave all their numbers fixed, because if this here doesn't leave a number fixed, this power here can't change that because it has nothing to do with the numbers of the other permutation. I hope this was clear. So here, very important to note that this is only true because the cycles are disjoint. And now we apply the hint here, the purple star. Maybe I should have better used numbers 1, 2, 3. Well, k is the order of sigma. Sigma to the s is the identity. This means that k must be a divisor of s. And, this here is short for and, the order of tau is l. Tau to the s is the identity, so l must divide s. So, s is a common multiple of k and l because both of them divide s, but m is the least common multiple. So by this property here, we already know that m, the least common multiple, must be a divisor of s. And now we are done, because s divides m and m divides s. This is only possible if m equals s. If you're not so familiar with divisibility, here you could also say s is less than or equal to m, obviously, and this here means that s is greater than or equal to m. And both taken together leave no choice but m being equal to s. Whew, that's it. That's the complete proof. Could you have done it yourself? If so, please comment and congratulations. Could you follow all the steps? Could you understand this step by step? This is already a big achievement. So I think this is nice because permutations per se seem kind of trivial. I simply write down numbers and shuffle them around, but already there's a lot of depth and beauty in this subject here. And to restate that, I really think this here has deserved the skull because this is exceptionally difficult for a true beginner. So if you couldn't solve it by yourself, but could follow all those steps, that's already good enough.